Welcome to this lesson on storage classes in C and C++ programming. Imagine you are organizing tools in a workshop. Some tools you keep in your pocket for quick use, while others are bolted to the floor permanently. In programming, variables are exactly like these tools, and we need a way to tell the computer how to store and manage them. Today, we will explore how storage classes give you precise control over memory management and data security. Now that we understand the workshop analogy, let us look at what a storage class actually does. Formally, a storage class defines four specific properties of a variable. First is scope, which refers to the specific region of the code where the variable can be accessed. Second is lifetime, dictating how long the variable exists before its memory is reclaimed. Third is the default initial value, which can be a safe zero or unpredictable garbage left over from previous programs. Finally, the storage location tells the compiler whether to place the variable in standard RAM or directly inside the high-speed CPU registers. Before we dive into each specific class, let us visualize where these variables physically live inside the computer. On the screen, you can see a diagram separating the ultra-fast CPU registers on the left from the standard RAM on the right. Notice how the register storage class is the only one that requests space in the CPU. Meanwhile, the auto class goes to a temporary scratch pad in RAM called the stack. The static and extern classes, which have permanent lifetimes, are stored in the data segments of RAM. Let us explore each of these four classes one by one. Starting with the most common storage class, we have auto, which stands for automatic. Whenever you declare a normal variable inside a function, the compiler automatically treats it as an auto variable. These variables are stored in standard RAM, specifically in a temporary area called the stack. Because their scope and lifetime are strictly local, they are completely invisible outside their curly braces and are destroyed the moment the function finishes. Crucially, if you do not give an auto variable a starting value, it will contain garbage data. You must always manually assign a value before using it, or your math will be ruined. Moving on from auto, we have the register storage class, which is very similar but comes with a special request for maximum speed. By using the register keyword, you ask the computer to store the variable directly inside the CPU's hardware registers instead of standard RAM. Historically, this was used for heavily accessed variables like loop counters. However, modern compilers have become incredibly smart and automatically figure out which variables should go into registers. Because of this, the register keyword has been deprecated since C++11 and removed entirely in C++17. You should no longer use it in modern code. Now that we have covered the temporary storage classes, let us look at the static keyword, which is incredibly powerful. When you use static on a local variable inside a function, it changes the variable's lifetime from temporary to permanent. Instead of being destroyed when the function ends, a static local variable stays alive in memory for the entire duration of the program. The next time you call that function, the variable remembers its last value instead of starting over. Even though it lives forever, its scope remains local, so no other function can touch it. Plus, it is automatically initialized to a safe zero. To see how this works mathematically, suppose we want to write a function that counts how many times it has been called. We declare a static integer variable, which we will denote as C. Before the function is ever called, the compiler automatically sets its initial state, C0, to exactly 0. This guaranteed zero initialization is a massive advantage over the auto storage class because it completely saves us from dealing with dangerous garbage data. If this were an auto variable, C0 could be any random leftover number, which would ruin our counting logic completely. Let us trace what happens when we actually run the code. When the function is called for the very first time, we want to increment our counter variable by 1. We take our initial state, C0, and add 1 to it. Substituting the guaranteed 0 value, we get 0 plus 1, which equals 1. So, at the end of the first function call, our static variable holds the value 1. If this were an auto variable, this value of 1 would be completely destroyed and lost the moment the function finished executing. Because our variable is static, that value of 1 is preserved safely in RAM. When the function is called a second time, the variable does not start over at 0. Instead, it picks up exactly where it left off. We use the preserved value, say 1, to calculate the new state. 1 plus 1 equals 2. The variable acts like a permanent memory band for the function, safely incrementing to 2, then 3, and so on, while remaining completely invisible to the rest of the program. It provides permanent memory with private access. We just saw how static works inside a function, but it has a second entirely distinct meaning when applied to a global variable. Normally, a global variable can be accessed by any file in your project. However, when you put the static keyword in front of a global variable, you change its linkage to internal. This means the variable is strictly locked down and visible only within the specific source code file where it is written. It acts like a private global variable for that one file, which is incredibly useful for preventing naming conflicts in large projects. This brings us to our final storage class, extern, which stands for external. You use this keyword when you want to share a single global variable across multiple different files. When you declare a variable with extern, you are not actually asking the computer to set aside memory. Instead, you are making a promise to the compiler that this variable exists and has memory allocated in some other file. Its scope is truly global. In this way, extern is the exact opposite of the global static variable. While static hides a variable, extern is the bridge that allows other files to access it. To understand the difference between global static and extern, imagine we are building a video game with a physics file and an enemy file. If we want both files to share the exact same speed variable, we define it normally in one file and use extern in the second file to link them. Let this shared speed be S1. Because extern acts as a bridge pointing to the exact same memory address, if the physics file changes the speed to 50, the enemy file instantly sees the value 50. They are sharing the data globally. This is how large programs efficiently manage shared state without duplicating memory. But what if we want the physics and enemy files to be independent? We use the static keyword at the global level to enforce internal linkage. If we declare the global variables as static in both files, the compiler creates two completely separate memory locations, even if they are both named speed in the code. Let the physics speed be S1 and the enemy speed be S2. The physics file can set its speed to 100 and the enemy file can set its speed to 20. They will never interfere with each other because S1 is not equal to S2. They are completely isolated. Now that we have seen all 4 storage classes in action, let us summarize their rules of engagement. For the auto class, the scope and lifetime are local, and it leaves you with dangerous garbage data if not initialized. The register class is similar but requests CPU storage. The static class provides a permanent lifetime and a safe 0 default, whether used locally for permanent memory or globally for file privacy. Finally, the extern class provides true global scope across multiple files, also guaranteeing a safe 0 default. Visualizing these properties makes it easy to choose the right tool for your data. To wrap up, storage classes are the invisible backbone of secure and efficient software engineering. They answer the critical questions of where a variable lives, how long it survives, and who is allowed to see it. Remember that auto ensures temporary data is quickly cleaned up, while register is deprecated in modern C++. Using static allows you to create modular, plug-and-play code files that do not pollute the rest of your project. And extern lets you share data when necessary. Mastering these tools transforms you into an architect who can precisely control the flow of data.